Hi, in this tutorial, I'll explain how to create inspections on 3D point components. In order to best demonstrate this topic, let's take a look at this sample project. Here we have a toy excavator with reference points applied on major components. For this example, we will consider the components of the excavator to be rigid. This allows us to assume that the reference points grouped on each component represent the movement of those components throughout the test. Our goal with this project will be to determine the position of each component and therefore the overall motion of the excavator throughout the project. Let's begin by focusing first on the undercarriage and superstructure of the excavator. Just like with stochastic patterns, components are the basis of our analysis. This time we'll use a type of component called point component. We can use measured reference points as the basis for point components. Each reference point receives a unique identification that applies to every stage in the project. More detailed information about point components can be found through the Direct Help question mark button. As soon as you open the Create Point Component dialog box, the measured points become visible in green. Our goal now is to create point components for each component of the excavator: the undercarriage, the superstructure, boom, extension arm, and bucket. First, select the points on the superstructure with Control and the left mouse button, or with Control and the left mouse button, click and drag. A selected point will appear red and become part of the points list in the dialog box. Click Create and follow the same steps to create a point component for the undercarriage, boom, extension arm, and bucket. The software tracks the point component in 3D space for every stage. Now, we need to create a reasonable alignment for our project. We could use a 3-2-1 alignment using the point component for the undercarriage, or we can use the included CAD model for the undercarriage in order to align our project. Click on the plus sign in the far right corner of the software to add a new 3-point alignment. Next, open the PIP window. Left-click on the CAD from the Overview Explorer and drag and drop it into the PIP to make it exclusively visible. Now hide the CAD in the 3D view by either clicking on it and hitting the I key on the keyboard, or by clicking on it in the Overview Explorer and either hit I or click on the I icon. Now, align the CAD model as close as possible to the position of the undercarriage in the image by using the same 3D manipulation clicks as in the 3D view. Now, hold down Control and left-click to select a nominal or CAD data point, followed by its corresponding actual point in the point component location. You will do this twice more. Once that is complete, set the CAD data to visible and check to make sure that the alignment looks accurate. You can click on the red X next to any of the points to remake a selection. Once you are satisfied with the alignment, click OK. You can now minimize the PIP window by clicking on its name. You can now analyze the displacement of the point components using the displacement inspection. Software creates vectors at each point showing the direction and magnitude of the displacement in 3D space. However, in most cases, you might be more interested in the relative motion of different components. When I show only the raw images and move through the timeline, you can see that as the superstructure and extension arm move, the undercarriage also has some slight movement. We can subtract this movement from all the others using a rigid body motion compensation. Let's first create a wide displacement inspection to better analyze what is happening. You can see that both the superstructure and undercarriage have some displacement in the y direction throughout the test. We can better visualize the amount of displacement by adding some deviation labels. Let's also create a specific stage range for the vertical movement of the excavator. Now, looking only at this stage range, let's also change the legend to display all visible stages. We can now easily see the movement of both the undercarriage and superstructure during the vertical movement of the extension arm and boom. To create the rigid body motion compensation, click on the plus sign for adding alignments and go to Transform by Component. Looking at the displacement vectors, you can see now that the vectors for the superstructure are smaller and the vectors on the undercarriage have disappeared. A rigid body motion compensation corrects the absolute movements in 3D space by the relative movement of another component. I'll expound on this concept further by making rigid body motion compensations on all the components of the excavator. You can switch between rigid body motion compensation at any point, but only one compensation can be active at a time. You can also create and inspect elements constructed from the point components. For example, we can construct and inspect the angle between the boom and the extension arm. First, we need to have point components for the boom and the extension arm. Next, we need to create two lines. We can do this by going to Construct, Line, Two-Point Line. Select 2 points with Control and the left mouse button to create a line. By clicking Create, the dialog box remains open so that we can create another line. Once the two lines are created, we need to create an angle between them by going to Construct, Angle, two directions angle. Select the two lines by finding them in the drop-down menu or by Control and left-clicking them in the 3D view. We can invert the directions using the buttons next to the direction names until we have the inner angle. We can now inspect the constructed angle for its magnitude by using the iInspect wheel. The iInspect wheel shows appropriate inspections for any selected element. So for our example, the angle. We can view the angle change on its label or in the Diagram tab. Now it's your turn. Practice the steps in this tutorial by opening GOM Correlate and selecting the 3D project, GOM Testing Object Motion Analysis, located in the sample data icon. Next, create point components for the undercarriage, superstructure, boom, extension arm, and bucket. You can find more information on point components through the direct help. Now create a 3-point alignment using the existing CAD model and the undercarriage point component you created. Make sure that the CAD model is exclusively visible in the PIP window, roughly aligned to the undercarriage in the 3D view, and hidden in the 3D view. With an appropriate alignment, you can now check the point components for the total and Y direction displacements. Practice changing the legend scaling to all visible stages. Create deviation labels on some of the displacement checks. Next, create a stage range for the vertical movement of the excavator and open it in the timeline. Create a rigid body motion compensation using the undercarriage. Find the angle change between the boom and extension arm by constructing a 2-point line on both the boom and extension arm and a 2-direction angle between these lines, and then check it for its angle. Use the selection tools in the 2-direction angle dialog box to select the angle of interest. Finally, create report pages displaying the Y direction displacement and angle change using the styles that best display the data. Create a separate report page showing how rigid body motion compensation using the undercarriage affects the Y direction displacement. Export these report pages as images or videos. If you feel comfortable with this exercise, feel free to start watching the next GOM Correlate tutorial, or for more information, visit trillion.com. In the next tutorial, we will go into more detail on reporting.